So hi, I'm Teresa and I will be explaining the anti-windup used in PID controllers. But what is PID? PID stands for Proportional Integral Derivative Action. A PID controller is a control loop mechanism employing feedback that is used in industrial control applications to regulate temperature, flow, pressure, and other variables. An integral windup is a process of accumulating the integral component beyond the saturation limits of its final control element. For example, if a set point rises, there will be a larger error between the set point and the actual value. This error causes the integral component to accumulate with the time period. It is necessary to bring the actual value back to a number near the set point. An integrator windup can be avoided by making sure the actuator doesn't saturate. The anti-windup scheme is known as tracking calculation. With Simulink, it's really easy to see. This system has an input saturation. In this graph, we can see the set point versus the measured output, that is in yellow, with no anti-windup. In this graph, we can see the set point versus the measured output with back calculation, meaning anti-windup. Let's compare both measured outputs. Here we can see both systems. The one in blue represents the one that didn't use anti-windup, and the one in orange represents the one that did use anti-windup. We can see how quickly the PID control signal returns to the linear region and how fast the loop recovers from saturation while using anti-windup. An example could be in a heat exchanger process. We can see in the graph that it exceeds the 200 degrees limit. To the left, we can see that there is a delay in the measured process variable response, the one that doesn't use anti-windup. And to the right, we can see that the measured process variable responds quickly and returns faster to 200 degrees, meaning that this area is bigger than this little area, meaning that it takes more time while not using anti-windup. So it is necessary to use anti-windup. Thank you.
Hi everyone, I'm Fernando and I'm talking about the zoning of PID controllers in a Ziegler-Nichols method. Well, first, we only can use the Ziegler method, the graph method, where we have a response of signodial. If there is another type of response, we can use this method. It's very simple. We have our function. So with this graph, we see the blue point, and where it's stabilized is where we have the gain. So we have key. We make a tangential line. So the start to the end, we have the tau, and the time it takes to start that tangential line is L. Then we have this table. It depends in which controller are you using. Now we're using a PID, so we need these values to generate this function. So now this is an example, very quick. It's very simple, this method. As we can see here, we don't know the process. We don't know the transfer function. So what we do is, with this graph, we see that it's stabilized at 2, so k is 2. We see that with our tangential line, it's 9, it's 11, but it starts at 2, so it's 9, the tau is 9. We replace it, and we need to see a controller checkpoint. You see, we can control the process. It is more than 0.3. We can't in this time. When we divide L by tau, we see that it's 0.2, so we can control it. Now we have defined our function, and we need to find the values of Kp, Ti, and Td for the process, for our controller. So we only need to use the table. To Kp, here is 1.2, tau divided by k times L. We found the values, and if we put it in Simulink, we can see how the scope will be. So it starts here, and it's stabilized, and this is how the Ziegler method 1 is made. Thank you for your attention.
So continuing to explain the controller tuning, we now pass to the minimization index criterion. We have the ISE, EAE, ESTE, and ETAE. So integral performance criterion mainly focuses on minimizing the error signal coming from the set point and the feedback. The desired goal of these processes is minimizing the values of the maximum overshoot, rise time, settling time, and the steady state error. So now talking about ESE and EAE, the integral square error and integral accumulated error is the simple integration of the error values in which the EAE stands for the absolute error while the SE stands for the squared error. So these processes weight all errors equally and independent of time and can result in a response with a really small overshoot but long sampling time or vice versa. And that's why we need to have the following processes that are the STE and ETAE. So now we consider the time in both cases, and that's why we have the time weight. And this is to overcome the problems of the ESE and EAE and control overshoot or the setting time if it's the case. But both procedures counts the error even if the error is in the late time values near to the steady state time. So to compare these two problems, we have the time weighted and the error without the time. We have that, for example, E increases in the time 10, but this can be better for the problem because we need to consider those late errors. We don't want to have a steady state error which is low because we want a great overshoot, but also vice versa is like a one for to consider in the problem. So for these two processes, the writing time, the maximum overshoot, the settling time, and the steady state error, and also gain margin and phase margin can be affected and might not be minimized by the problems with the time weight, but we have for that case the other unweighted errors. So this is, for example, to fit problems in which the ETSE or ETAE cannot reduce the overshoot or have a higher error in the steady state. So now for an example, we will consider this following fourth order system. Now our code and comparison. This code does a simple integration of the function of the approximated error values, trying to reduce this overshoot, the writing time, and also the settling time. So MATLAB makes it easy to call the different processes, the different methods. We have that 3,1 calls for an ESE index, 3,2 the EAE index, the 3,3 calls the ITSE, and the 3,4 calls the ITE. So we have these different graphs in the part above in which we are comparing it to the Ziegler-Nichols method, and we see how the different processes reduces this settling time and maximum overshoot in ways that are better than the Ziegler-Nichols. However, between them we have variations. In this case, the ITSE is the best fit for the problem. However, this is not always the case. It's a good method to use, but sometimes even the time-weighted methods have their own problems. So we can use this code that easily makes them the visualization for the problem, and that we have these equations in C1, C2, C3, and C4. The values we can solve easily the tune for the different problems that we have.